Hello, my name is Shazeb and today I'll be presenting on image enhancement techniques. Before learning the concept of image enhancement, we'll know a little bit about image processing. Image processing is some kind of algorithm that needs to be performed on an image so as to use it for some kind of purpose. Image processing is a highly developing field in the field of machine learning or artificial intelligence. Well, before applying this image processing, we have to pre-process the image. One kind of pre-processing that we'll learn about in today's slide is image enhancement. In this slide, we'll learn about image enhancement by image averaging. On the bottom of the slide, you can see the result of applying this technique. On the bottom of the slide, the picture, we can see on the left hand side the initial image, but after averaging out, the result is as shown on the right hand side. The initial image was containing a lot of noise, but after it has been averaged, it was containing less noise. In the above algorithm, we can see if f of ij is the pixel value at a corresponding ith or ith row and jth column, and nk of ij is the corresponding noise value at ith row and jth column, then g of ij is the result of applying this algorithm at ith row and jth column. Suppose the variance of the noise initially was sigma n, and the variance of the noise after the output of this algorithm is sigma n prime. Then we can clearly see from this slide that after it has been averaged, the variance reduces by a factor of root n. In this slide, I'll tell you about brightness and contrast. Brightness of an image is the overall intensity of the image. The more the amount of intensity present in the image, the more the brighter the image will be. Suppose we are taking a grayscale image that has intensity values mapping from 0 to 255. If it has pixel values correspondingly mainly to 255, then we will call it as a bright image. Or if it has pixel values nearby to 0, then we'll call it as a dark image. Well, what contrast is the presence of different kind of brightnesses in the image. Suppose in the image we have the 255 pixel value and also the 0 pixel value. Then we'll call it a more contrasted image rather than the image having only 255 pixel values or 0 pixel values. Here in this slide are the formulas of brightness and contrast of the image, where M and N are the dimensions of the image in the x and y axis for the grayscale image, and f of I, j is the corresponding intensity or pixel value. Most of the image enhancement techniques nowadays require the help of image histograms. Well, what an image histogram is it tells you about the probability of finding a particular intensity value. In this histogram, in this slide, we can see that on the x-axis we have the intensity values, and on the y-axis we can see the frequency of occurrence of that particular intensity value. Rather than understanding histogram as the frequency of occurrence of that intensity value, we can also keep in mind that it can be understood as the probability of occurrence of that particular pixel value. So here are the three histograms for a dark image, a bright image, and a well-balanced image. Here in this slide, we can see an image with a low contrast and an image with a high contrast after applying some techniques to the histogram. For the previous slide, the histogram of the images are plotted. On the left hand side, we can see the histogram for the original image, and on the right hand side, we can see the histogram for the image that has been applied some kind of transformation so as to increase its contrast. Well, this particular histogram on the right has been derived after applying a common technique called as histogram equalization, which we'll talk about in the later slides. To change the value of histograms, we'll apply a mapping function g of f to all the pixel values of the original image A. So b of I, j is the new pixel values after applying the transformation g of f to the corresponding image A of I, j. One kind of technique to change the histogram is to apply a linear mapping function of type AF plus B. Suppose the initial image has been intensity values ranging from S1 to S2, but we want our final image to have intensity values from T1 to T2. Then, so to do that, we'll use this linear stretching function and derive so as to get A as T2 minus T1 upon S2 minus S1 and B as T1 minus S1 into T2 minus T1 upon S2 minus S1. In this slide, we have applied the linear stretching technique on the image present on the left hand side. The output is the image present on the right hand side. P of f is the probability of occurrence of frequencies of the initial image, and P of g is the probability of occurrence of frequencies of the final image. Clearly, we can see after applying the linear stretching function g of f, we have increased the span of g. Some nonlinear stretching techniques use the help of the functions logarithmic transition, exponential transformation, or use of power functions. Here we have applied nonlinear stretching technique logarithmic function to the histogram present on the left hand side so as to get a new histogram present on the right hand side. Histogram equalization technique is a technique so as to transfer the gray levels towards all of the intensity values. Suppose the initial gray levels were only present for the higher intensity values, but after applying the histogram equalization technique, we can see the gray levels will also be present in the lower intensity values so as to increase the contrast of the image. Histogram equalization can be understood from the image present in this slide. The figure shows that for any given mapping function y is equals to f of x between the input and output images, the following things hold is that dy is equals to p of x dx, where p of x is the initial probability density function and p of y is the final probability density function after applying the transformation y is equals to f of x. So, to normalize the histogram, clearly we can see p of y should be equals to 1. So dy by dx will be equals to small p of x. Now we can integrate this function to get our transformation function y is equals to f of x. We'll assume y is equals to f of x to be equals to capital P of x after we have integrated the function dy by dx is equals to small p of x. If p of x is high, that is, if small p of x is high, then the capital P of x has a steep slope, that is, dy will be wide, causing small p of y to be low to keep small p of y dy is equals to small p of x dx. If small p of x is low, capital P of x has a shallow slope and dy will be narrow, causing small p of y to be high. So we can clearly see that if the intensity values were present only in the higher region, then this probability density function has been changed so as to so as to introduce all the pixel values also in the darker regions. In image processing, a kernel is a kind of matrix that is applied to the initial image so as to produce a new image that has been enhanced. A kernel is convolved with the initial image. Here are some of the kernels that can be convolved to our image, which are the mean kernel, the Gaussian kernel, and the Sobel kernel. Mean kernel can be used to reduce the noise. Similarly, Gaussian kernel can also be used to reduce the noise. The Sobel kernel is used for edge detection. Convolution is a technique to multiply two matrices together. Suppose we have our initial image as m cross n and a kernel size as f cross f, then we can multiply the corresponding intensity values of the kernel and the convolution and the initial image and add them up together to form the convoluted image. Here is the convolution technique that is applied to the source pixels by the convolutional filter or the kernel Sobel g of x. This is a filter or a kernel to detect the edges present in the image. The filter is multiplied with the initial images and the result is added up. Clearly, we can see after multiplying and adding up together, our result is -3, the corresponding given example. After it has been multiplied to a particular set of source pixels, then it is strided towards the right hand side and then again multiplied by the corresponding new pixel values and the new destination pixel is calculated. Gaussian blurring is a technique to blur the image. The transformation function given on the bottom of the slide g of x, y can be applied to the image values so as to get the new Gaussian image that has been blurred. Instead of applying the Gaussian function to the intensity values of the initial image, we can convolve the given image with the given filter on this slide so as to get the output same as directly applying the transformation function. Here is the result of applying or convolving the Gaussian kernel with our initial input image. Well, not only Gaussian kernels, there are many kinds of kernels that can be convolved with our initial image so as to get the new output image that has been enhanced. Thank you.